If we take two very complicated three-dimensional surfaces which are defined by polynomial equations and then shove them so that they're right on top of each other, then their intersection is going to be some kind of a curve, and it's going to be a very complicated curve. But each of those curves, the way in this new perspective it's going to work is that each of those curves is going to be completely equivalent to us just standing at the origin and kind of like moving our head and looking around. And that's going to have this ray of light. It's going to trace out this complicated path. And those paths that are equivalent to us moving our head around and just kind of looking around, instead of dealing with really complicated curves where two surfaces intersect, it's going to be really nice because every intersection is just going to be us standing there looking around. So, for example, if we're just like looking out at this angle, whatever it is right now, if we just keep our head and our eyes totally fixed, and then we just rotate around so that that ray of light's going to trace out a cone. And then we're going to take a plane in this three-dimensional space, and we're going to stick it like flat above us so that it intersects with that cone. Whereas before, in the other perspective, we were moving the sphere through the floor, now what's happening is that we're just going to stand still and move the ceiling up and down. So instead of thinking about rays of light coming from the ceiling and hitting us in the eye, now what's going on is we have laser eyes, and every part of the ceiling that we look at, it's like we're painting on the ceiling because it's burning a hole in the ceiling basically, and then we're looking with our laser eyes around, and it's tracing out this curve on the ceiling from us just looking at it. And that path is what's called a parameterized curve. What we'd really like to do is back in the real world where the sphere was actually going through the floor, is we'd like to be able to describe the intersection, which is this curve, with a parameterized curve. And so one of our goals when we're solving systems of polynomial equations, the solutions, instead of being distinct set of points, now the solutions are these continuous curves. We want to find a parameterized way to like actually draw the curve. But we need a formula to do that. In order to understand why this new perspective is so helpful, we really need to understand a little bit more about parameterized curves. The first thing we want to notice is that for any given curve, we can just measure the length of the curve. We're going to call the total length of the curve S, and then we're going to calculate S by using the mini Pythagorean theorem. That's a really good way to remember the formula for the arc length of a curve. And then a really nice choice for our parameter is going to be what's called the arc length, which means that it's just how far along the curve we've gone already. So let's take a closer look at the arc length and why we want to parameterize our curves like that. First of all, we need to fix this equation up because t generally means time. If you're like drawing and you just drank a lot of coffee and you're drawing this curve and then you draw it really, really fast, then that's one kind of fast drawing time. But then also maybe what you did, you were in math class and you just started doodling a picture of this curve in your notebook, and then you asked the teacher a question, and then after that you finished drawing it. We need to make sure that when we're drawing the curve, that the amount of time it takes to draw is exactly the same as the amount of length of the line that we drew. That's what it means to parameterize by arc length. Basically, the t is for time, and that's when we're allowed to move around this curve at different speeds. But s means arc length. So let's get those t's and turn them into s's. That's going to be step one. Now that we have our curve parameterized by arc length, let's measure the length of the whole thing. What's really important to notice here is that since s is equal to the integral of the length of d gamma, that ds is equal to the length d gamma. And then when we take the derivative with respect to s, we're going to find out that the length of d gamma ds is equal to 1. And that means that when we parameterize our curves with arc length, that the tangent vectors are going to actually be unit vectors. And that's really convenient. You might wonder where the idea of a unit tangent vector came from. Since we're just dealing with plane curves, or in other words, curves that just live in the complex plane, we're just going to use the imaginary number I and treat it like a vector. The arc length is what's called an invariant of the curve. And that's because if you take a certain curve and then translate it around and like rotate it and stuff, the length is not going to change. And there's another invariant of the curve which plays a really fundamental role, and that's what's called the curvature. What we'd like to do is associate every curve with what's called its circular image. Maybe a good way to do that is to just forget about the curve completely, and then we're only going to look at this tangent vector, the unit tangent vector d gamma ds. Since d gamma ds is a complex number that has absolute value equal to 1, we can write d gamma ds as the exponential of I times some angle theta where theta depends on s. The function theta of s is what's called the circular image of the curve. As the parameter s is varied, then the curve gets traced out, and the tangent vector at any point is going to rotate around back and forth. And we're going to represent this curve now. It's just going to be a point that's on the unit circle and is constrained to only move on the unit circle, and it's going to rotate by the same angle that the tangent vector is rotating as the curve is being traced out. And that's going to enable us to define the curvature of the curve and the curvature at any point. The curvature along any finite portion of the curve is by definition equal to the difference between the angle of the tangent vectors from the final position and the initial position. Then the average curvature for that portion is defined as that curvature divided by the length of that portion. And this is going to enable us to define the curvature at any given point along the curve by taking the limit as that length goes to 0. Let's see how the tangent vector is related to the curvature. If we take the derivative of both sides of this expression and then take the absolute value, then we immediately see that the length of the second derivative of the curve is equal to the average curvature. And if we have a function which gives us the curvature of a curve for every point, then that curve is uniquely determined. What this theorem is telling us is that a curve is truly characterized by two things, its arc length and its curvature. And a good way to think about that is that instead of just finding the line, which is the best fit approximation to the curve at any point, the curvature represents the best fit approximation circle to the curve at that point. And now, if we're standing on the ground and we're shooting laser eyes out at the ceiling now, and we want to move our head, we can just use spherical polar coordinates, theta and phi. And theta is just going to be the circular image, and phi is just going to be s.